The Lagoon Nebula is a vast cosmic cloud where new stars are being born right now. But what secrets hide within its glowing gas and dark dust? In this video, we'll journey deep inside one of the galaxy's most breathtaking nurseries of creation. If you enjoy it, please like, subscribe, and share, and tell us in the comments, what would you ask if you could stand beneath these newborn stars? Thank you for watching. Now let's begin. The Lagoon Nebula appears as a vast glowing region of space dominated by the light of ionized hydrogen gas. Ionized hydrogen means hydrogen atoms that have lost their single electrons because of the intense ultraviolet radiation from nearby massive stars. When the electrons later recombine with protons, they release photons often in the deep red part of the visible spectrum. This red light fills the nebula with a diffuse glow. The area covered by the Lagoon Nebula is large when measured from Earth several dozen light-years across, making it one of the most striking emission nebulae in the night sky. Its shape is not uniform but has bright regions, dark channels, and irregular contours that all reveal the combined effects of radiation, winds, and gravity. The dominant cavity of ionized hydrogen forms the main stage on which these processes play out. In this cavity, the gas is heated to thousands of degrees Kelvin, a measure of absolute temperature, where 0 Kelvin means no thermal motion at all. At such high temperatures, the hydrogen stays ionized and continues to emit light. The surrounding gas is less heated, creating gradients in density and temperature. These gradients control how material expands and how shock fronts move. The cavity has sharp edges in some directions where radiation pressure has compressed cooler gas into dense ridges. In other places, the boundaries are diffused with soft transitions into more tenuous material. This unevenness reflects how stars inside the cluster produce radiation at different rates, and how their winds interact with the surrounding medium. The Lagoon Nebula lies within the Sagittarius arm of our galaxy, at a distance estimated to be about 4,000 to 5,000 light-years from Earth. That estimate has an uncertainty because parallax and spectroscopic measurements give slightly different results. Still, astronomers agree that the nebula belongs to the same spiral arm where many other large star-forming complexes are found. Its location is not isolated, but part of a larger pattern of gas dust and clusters in the galactic plane. The nebula therefore both receives material from the larger interstellar environment and contributes new stars and feedback into it. Looking into the central ionized region reveals multiple types of light beyond visible red emission. When viewed in green light from doubly ionized oxygen, or in blue light from ionized helium, additional structures appear. Each spectral line corresponds to a different atomic transition, providing astronomers with tools to measure physical conditions. For example, the ratio of oxygen and hydrogen lines can indicate electron density, while helium lines show temperature variations. The cavity of the Lagoon Nebula thus becomes a laboratory, where basic plasma physics occurs on scales far beyond any human-made device. Radiation escaping from the cluster does not move through empty space, but constantly encounters pockets of dust and denser gas. Dust grains absorb and scatter light, producing dark patches within the glowing nebula. The central cavity remains bright because enough radiation clears dust along our line of sight. At its edges, however, curtains of dust partly block emission, giving the appearance of uneven illumination. These contrasts help define the three-dimensional structure. Where dust is thickest, the nebula appears cut by lanes and streaks, but in this first view, the broad glowing expanse is dominant. The brightness of the Lagoon Nebula is not constant across time, but varies subtly as new stars form and as winds reshape the gas. Over hundreds of thousands of years, which is rapid in astronomical terms, the cavity will expand further. Gas in the central region may eventually disperse, leaving behind the star cluster as a more exposed group of young stars. For now, the cavity demonstrates how powerful radiation alone can be in transforming the interstellar medium. Even without strong winds or supernovae ionizing photons, carve large volumes of space into glowing shells. Observing this region requires careful calibration because ionized hydrogen emission lines coincide with emissions from the Earth's own upper atmosphere. Astronomers use narrow band filters that select only the nebular lines while subtracting sky background. Images taken with these filters reveal the detailed distribution of hydrogen gas, showing knots, arcs, and ripples within the cavity. Spectroscopy adds velocity information, allowing measurement of how fast the gas expands. Velocities of several kilometers per second are common, which over millions of years transport matter across entire light years of distance. The cavity does not only emit light, it also influences star formation nearby. Radiation pressure and expanding shells compress adjacent clouds, raising their density. In some places, that compression may push clouds beyond the threshold, where gravity can cause collapse into new stars. In other places, the energy input instead disperses the material, halting star formation. This dual role of feedback remains an area of research. The Lagoon Nebula provides a natural case study because it shows both triggered collapse and regions of dispersed gas side by side. Within the central cavity reside the most massive stars of the cluster. Their ultraviolet radiation is the main cause of ionization. Among these stars is one especially bright O-type star, several tens of times the mass of the Sun. Such stars are rare and short-lived, burning their fuel at high rates and living only a few million years. Yet during their brief lifetimes, they dominate their environments. Without them, the Lagoon Nebula would be far fainter. The central cavity would shrink, and dust would not be pushed aside. Thus, the existence of one or two massive stars determines the appearance of the entire nebula. Gas in the cavity also emits radio waves, particularly from electrons spiraling around magnetic fields. These radio signals confirm that the cavity is filled with plasma, a state of matter where charged particles move freely. Radio observations complement optical images by revealing regions hidden by dust. Together they form a consistent picture of a hot ionized bubble centered on young stars. That bubble extends for many light years, and from Earth it subtends an area large enough to be seen with small telescopes. Amateur astronomers can view the Lagoon Nebula as a faint patch in Sagittarius, while professional instruments dissect it into detailed structures. When looking at the cavity in infrared light, warm dust glows, outlining regions where radiation heats grains to a few hundred degrees Kelvin. These grains are smaller than a micron in size, yet they control much of the absorption and re-radiation of starlight. In the cavity, their abundance is reduced because grains are destroyed by energetic photons. At the edges, dust remains intact, producing strong infrared emission. This contrast between a dust-poor cavity and dust-rich rims illustrates the ongoing cycle of destruction and survival within star-forming environments. The interplay of light and gas creates a scene both complex and systematic. The rules of physics such as ionization, recombination, and radiation transfer apply uniformly, yet local variations in density and star positions lead to intricate patterns. Observers can trace arcs where shock fronts move, identify pillars where denser gas resists erosion, and measure cavities where light has cleared channels. Each feature is a direct expression of physical laws acting on cosmic scales. In the Lagoon Nebula, The central ionized cavity provides the first and clearest example of this process. It is the environment from which the rest of the nebula's features grow and evolve. Across the glowing expanse of the Lagoon Nebula lie broad dark lanes and narrow filaments of dust that stand out against the red emission of ionized hydrogen. These features are not empty space but dense collections of microscopic grains made of silicates, carbon compounds, and ices that absorb and scatter light. Because the background emission is bright, even modest amounts of dust produce sharp contrast, appearing as dark streaks and blotches across the nebula. The dust lanes stretch for many light years, crossing the glowing cavity and dividing regions of emission into distinct zones. The filaments are finer, sometimes less than a light year across, and twist through the gas like thin threads. Both lanes and filaments represent reservoirs of cold material where star formation may occur if gravity overcomes turbulence and pressure. The physical size and shape of these dusty structures depend on both internal and external forces. Gravity pulls matter together while radiation from nearby stars pushes it away. Where radiation is strongest, dust grains are destroyed or expelled, leaving bright open windows. Where gas and dust are shielded inside thicker regions, filaments persist, casting long shadows. Observations show that some of these dark features point back toward massive stars in the cluster, indicating that they are shaped by direct radiation. The heads of such filaments are denser and rounded, while their tails stretch away in elongated forms. This geometry suggests ongoing erosion, with material slowly being ablated from the surface and carried downstream. Embedded inside the dust lanes are small clumps called globules. Each globule contains gas and dust dense enough to block nearly all background light, forming tiny black patches even in deep exposures. Some globules harbour young stars that shine faintly in infrared wavelengths, but remain invisible in visible light. Their presence reveals that these dark features are not passive shadows but active nurseries. Infrared surveys detect protostellar outflows and jets emerging from inside them, confirming that collapse and starbirth occur behind the veils. Thus, the lanes and filaments are more than mere obscuring bands. They are the very locations where the next generation of stars is taking shape. The interaction between dust lanes and ionized gas is particularly clear at the borders where bright rims meet dark interiors. These edges often glow with thin, sharply defined arcs of emission. The arcs occur where ultraviolet photons from massive stars strike the surfaces of dense clouds. The outer layers of the clouds become ionized, producing a skin of emission that outlines the shadowed core. Over time, the radiation eats into the cloud, compressing it and driving material away. This process can either stimulate collapse within the remaining core, or erode it completely depending on balance between gravity and radiation pressure. The Lagoon Nebula offers examples of both outcomes, with some filaments containing stars in formation and others gradually dissolving. Spectroscopic studies reveal the motion of gas in and around the dust structures. By measuring shifts in emission lines, astronomers determine velocities of a few kilometers per second relative to the surrounding cavity. These measurements show that filaments are not static but flow and twist under the influence of turbulence, winds, and magnetic fields. Turbulence stirs the gas-breaking filaments into knots and clumps. Stellar winds push them into arcs. Magnetic fields thread the material, aligning dust grains and guiding motion along invisible lines of force. The result is a dynamic environment where every filament changes slowly over time, even though the overall appearance remains recognizable on human timescales. Observations in different wavelengths reveal distinct properties of these dark features. In optical light, they appear as silhouettes against the bright nebula. In near-infrared light, they become more transparent, allowing astronomers to peer into their interiors. Their faint stars emerge that are otherwise hidden. In far infrared and sub-millimeter wavelengths, the dust grains themselves emit radiation due to their low but finite temperatures of tens of Kelvin. These emissions provide direct information on column density and mass. Radio telescopes detect molecules such as carbon monoxide within the lanes, mapping cold gas that fuels star formation. Each method adds a layer of understanding, building a complete picture of how these filaments function within the nebula. The dust lanes are also important for the overall energy balance of the region. By absorbing ultraviolet and visible photons, they re-radiate energy in the infrared, redistributing heat. Without them, much of the radiation from massive stars would escape freely. Instead, dust captures part of that energy, moderating conditions and influencing where new stars may form. The interplay of absorption and emission thus controls both the structure and the thermal state of the nebula. In regions with more dust, gas stays cooler, allowing gravity to act more effectively. In cleared regions, gas remains warm and diffuse, resisting collapse. This patchwork of conditions across the Lagoon Nebula explains why star formation occurs in specific pockets rather than uniformly throughout. From Earth, the most prominent dust lane appears to cut across the nebula, almost like a wide river separating bright areas into northern and southern zones. This impression is enhanced by the high contrast between glowing hydrogen and the dark band. However, the lane is not a flat sheet but a three-dimensional structure with varying depth. Some portions lie in front of the emission, while others sit deeper within. Careful mapping through parallax and velocity measurements shows that the geometry is complex, with overlapping filaments at different distances along the line of sight. Such complexity challenges attempts to create a simple model of the nebula, but also provides insight into how interstellar clouds assemble and fragment. At smaller scales, the dust filaments contain intricate details. High-resolution images from the Hubble Space Telescope reveal knots only a few thousand astronomical units across each, potentially harboring a protostar. Narrow tendrils of dust stretch from these knots, shaped by radiation and winds. Bright edges outline their borders, demonstrating the constant battle between external erosion and internal gravity. Some knots show tiny jets or outflows, indicating that collapse has already reached the stage of star formation. These observations highlight the active nature of what otherwise appear to be static, dark shapes. Even within their obscurity, dynamic processes unfold. The presence of dust also influences how we see stars in the embedded cluster. Light from young stars must pass through varying amounts of dust before reaching Earth, causing reddening and dimming. Astronomers correct for this effect by comparing observed colors with expected stellar spectra, thereby estimating dust density along each line of sight. This method reveals that extinction is patchy, with some stars nearly unobscured and others hidden behind thick curtains. The uneven distribution complicates efforts to determine cluster properties such as age and initial mass function. Yet it also provides direct evidence of how the nebula's dust interacts with starlight. The broader role of dust lanes and filaments extends beyond the Lagoon Nebula. Similar features appear in other star-forming regions such as the Orion Nebula and the Carina Nebula. Comparing these regions shows that dark filaments are a universal outcome of the balance between radiation, gravity, turbulence, and magnetic fields. The Lagoon Nebula serves as one local example where these processes can be studied in detail thanks to its relative proximity and brightness. By examining how its dust features evolve, astronomers learn general lessons about the birth of stars across the galaxy. In summary of this continuous view, the dark lanes and fine filaments across the Lagoon Nebula are not voids, but dense active structures that define much of the region's character. They obscure and reveal resist and yield shield and collapse. They create the striking contrast that makes the nebula so visible from Earth, while also concealing the delicate beginnings of new stars. Their presence is essential to understanding both the appearance and the ongoing activity within this vast star-forming complex. At the heart of the Lagoon Nebula lies the open cluster catalogued as NGC 6530, a gathering of hundreds of young stars embedded within the glowing gas. An open cluster is a loose group of stars formed together from the same cloud of gas and dust, sharing a common age and initial chemical composition. In the case of NGC 6530, the cluster is only a few million years old, making it very young on astronomical timescales. Many of its stars are still in early stages of evolution, burning hydrogen in their cores, while surrounded by remnants of the birth cloud. Their collective radiation fills the surrounding cavity with light and heat, and their winds continually drive changes in the gas. The cluster contains a mixture of stellar types from faint red stars only a fraction of the Sun's mass to massive blue stars, tens of times more massive than the Sun. The most massive among them dominate the energetics of the region. These O-type and B-type stars emit intense ultraviolet radiation that ionizes hydrogen across tens of light years. Without them, the Lagoon Nebula would not shine so brightly in visible light. The smaller stars, although numerous, contribute far less energy individually. Still, they are important as they represent the bulk of the stellar population and the seeds for planetary systems that may persist long after the massive stars expire. Astronomers study clusters like NGC 6530 to learn about the process of star formation and early stellar evolution. Because the stars share a common origin, differences among them primarily reflect mass rather than environment. This allows scientists to construct a sequence of stellar properties from low mass to high mass within one setting. Observations in optical light show the brighter cluster members directly, while infrared observations reveal fainter stars hidden by dust. The full census includes several hundred confirmed members, though deeper surveys may add more. The cluster is therefore not a single bright object, but a crowded field of stars of various luminosities and colours. The most prominent star in the cluster is an O-type giant often referred to as Herschel 36. This star is more than 20 times the mass of the Sun and emits several 100,000 times more energy. Its ultraviolet radiation alone creates the hourglass-shaped cavity at the centre of the nebula, sculpting the gas into a narrow waist and broad lobes. Herschel 36 has a surface temperature of tens of thousands of degrees Kelvin, producing both ionizing photons and strong stellar winds. These winds, consisting of streams of charged particles moving at thousands of kilometers per second, carve channels through the gas and drive shock fronts outward. Herschel 36 is also thought to be a multiple system with close companions that complicate its energy output and create variability in its surroundings. Surrounding the most massive stars are dozens of B-type stars, each several times more massive than the Sun. These stars also contribute to ionization, but at lower intensity. Together they form a collective field of ultraviolet radiation that floods the nebula. The lower mass stars, in contrast, are primarily visible through their infrared emission. Many are still surrounded by circumstellar disks of gas and dust from which planets may eventually form. Observations with the Spitzer Space Telescope, and more recently with the James Webb Space Telescope, have revealed disks glowing in mid-infrared wavelengths, confirming that planet formation material exists even within this harsh environment. How such disks survive the radiation of nearby massive stars remains an active area of research, but evidence suggests that at least some can endure long enough for planets to take shape. The cluster's stars are not evenly distributed but concentrated in a dense core with looser associations spreading outward. This spatial structure likely reflects the original fragmentation of the parent molecular cloud. Within the core, gravitational interactions between stars are strong, leading to close encounters and potential ejections. Some stars may already have been flung out of the cluster, moving away at high velocity. Such dynamical evolution is common in young clusters and may explain why open clusters generally disperse after a few 100 million years. For now, NGC 6530 remains tightly bound, and its collective gravity holds the members together. Light from the cluster illuminates the surrounding gas, producing both bright emission and dark silhouettes. Pillars and globules point toward the central stars, demonstrating the directional influence of radiation. By analyzing the orientation of these features, astronomers trace the geometry of radiation fields. The fact that many point toward Herschel 36 underscores the dominance of that star. At the same time, secondary features indicate contributions from other cluster members. Thus, the appearance of the nebula encodes the combined output of multiple stars, though weighted heavily toward the most massive. Spectroscopic surveys of the cluster provide information about stellar ages and compositions. The stars show nearly solar metallicity, meaning they contain similar proportions of elements heavier than helium as the Sun. This indicates that the nebula formed from gas already enriched by previous generations of stars in the galaxy. Age estimates place the cluster at about 1 to 2 million years with some uncertainty. Such youth means many stars are still contracting toward the main sequence, the stable phase of hydrogen fusion. These pre-main sequence stars often display variability in brightness, accretion signatures, and strong infrared excess from surrounding disks. Monitoring their light curves provides direct evidence of early stellar processes. X-ray observations with the Chandra X-ray Observatory reveal that many cluster members are strong X-ray emitters. Young stars produce X-rays through magnetic activity in their outer atmospheres, where rapid rotation and convection generate powerful fields. Massive stars, by contrast, emit X-rays primarily through shocks in their stellar winds. These high-energy emissions penetrate dust and provide a complementary view of the cluster. They also contribute to the ionization and chemistry of the surrounding gas. The presence of widespread X-ray activity in NGC 6530 reinforces the picture of a turbulent energetic environment where multiple feedback mechanisms act simultaneously. The cluster's role in shaping the Lagoon Nebula is central. Its radiation maintains the ionization of hydrogen, its winds sculpt the gas into cavity and pillars, and its gravity holds together the most massive stars. Without the cluster, the nebula would simply be a dark molecular cloud, invisible in visible light. With the cluster, it becomes a brilliant emission region, and one of the most recognizable features of the Milky Way. For astronomers, NGC 6530 serves as a living example of how clusters form and how they transform their environment. By studying it, they gain insight into the earliest phases of stellar life and the collective impact of young stars on the interstellar medium. The future of the cluster involves further evolution driven by its most massive members. When stars like Herschel 36 exhaust their nuclear fuel, they will explode as supernovae, injecting heavy elements and shock waves into the region. Such explosions will eventually clear away much of the remaining gas, ending the visible nebula phase. The cluster itself will survive, though likely looser and more dispersed. Over hundreds of millions of years, it may blend into the general field population of the galaxy. For now, however, it remains embedded in its birth cloud, shining brightly and shaping the Lagoon Nebula into its current form. The light from the young stars of the Lagoon Nebula does more than simply illuminate space. It exerts pressure on the surrounding gas and dust, producing physical changes that can be measured and traced. Radiation pressure is the transfer of momentum from photons to matter. Although a single photon carries little momentum, the immense numbers of photons streaming outward from an O-type star create a cumulative effect. When ultraviolet photons strike hydrogen atoms or dust grains, they push the material outward, gradually driving expansion. In the Lagoon Nebula, this process shapes the sharp edges of bright regions, forms curved arcs, and creates clear cavities. The most dramatic example is the central cavity around Herschel 36, where radiation pressure clears out a bubble tens of light-years across. The mechanism begins when photons ionize hydrogen atoms. Each ionization deposits energy into the gas, raising its temperature. Hot gas expands, generating pressure that pushes against cooler surroundings. The expansion sweeps gas into thin shells that mark the edges of the cavity. At the same time, dust grains absorb and scatter radiation, feeling a direct push outward. Because dust is embedded within gas, collisions between grains and atoms transfer momentum, causing the entire mixture to move. Over time, this combined action of ionization, heating, and photon pressure sculpts the nebula into its observed shapes. The most striking boundaries occur where gas density is high, because dense material resists expansion until pressure builds enough to drive a shock front. These fronts glow brightly in hydrogen emission, appearing as sharp rims or walls of light. The edges of the Lagoon Nebula therefore reveal the balance between outward radiation pressure and inward gravitational pull. In some places, radiation dominates, and gas is swept away into arcs. In other places, gravity holds dense clumps together, leaving behind pillars or globules that protrude into the cavity. These surviving structures are often referred to as photoevaporation remnants. Their surfaces face the cluster directly glowing, as they are continually eroded while their interiors remain shielded. The contrast between cleared regions and resistant clumps illustrates the uneven distribution of matter in the parent molecular cloud. Where the original cloud was denser, radiation pressure could not entirely clear the gas, leaving dark silhouettes against the bright background. The strength of radiation pressure depends heavily on the mass and temperature of the central stars. An O-type star like Herschel 36 radiates more than 100,000 times the luminosity of the Sun, with a significant fraction of that in ionizing ultraviolet photons. These photons travel until they encounter gas-producing ionization fronts that march outward at speeds of several kilometers per second. Observations of emission line profiles confirm that gas in the Lagoon Nebula is moving outward at such speeds consistent with models of radiation-driven expansion. Over millions of years, these expansions can enlarge cavities by dozens of light-years, reshaping the cloud into a bubble structure surrounded by compressed shells. The compressed shells along the edges of cavities are not merely passive features. Their increased density makes them prime sites for further star formation. When radiation sweeps gas into a ridge, gravity within the ridge may overcome turbulence, leading to collapse. This triggered star formation is one of the central topics in nebula studies. In the Lagoon Nebula, observations indeed show new stars forming along bright ridges, and ionization fronts suggesting that radiation pressure not only disperses gas, but also stimulates the birth of additional stars. However, the efficiency of this process remains uncertain. Some compressed regions collapse while others disperse before star formation occurs. The outcome depends on local conditions such as density, magnetic field strength, and the intensity of radiation. Detailed imaging of the Lagoon Nebula reveals pillar-like structures pointing toward the cluster. These pillars are dense columns of gas left behind as radiation carves away surrounding material. Their tips are often capped with bright rims marking active ionization fronts. Embedded within the tips are sometimes protostars detected in infrared and radio observations. This configuration suggests that radiation pressure can compress clumps to the point of collapse, leading to star formation within pillar heads. The famous pillars in the Eagle Nebula are similar in structure, and the Lagoon Nebula provides another example of the same phenomenon on a comparable scale. The presence of such pillars demonstrates how radiation sculpts not only the overall cavity, but also finer details within the cloud. The interaction between radiation and dust grains is particularly important. Dust absorbs ultraviolet and visible photons, re-emitting the energy in infrared. Each absorption transfers momentum to the grain, producing a gentle push. While the force on any single grain is small, the combined effect on vast numbers of grains within a cloud can be significant. In regions near the cluster, grains are accelerated outward, dragging gas with them through collisions. This dust-driven flow contributes to the clearing of central cavities. Infrared images from the Spitzer Space Telescope show arcs of warm dust outlining such flows, confirming their role in shaping the nebula. Radiation pressure also produces turbulence. As photons push gas unevenly, different regions accelerate at different rates. This generates shear and instabilities, which break up smooth fronts into ripples and knots. Observations of the Lagoon Nebula show many such rippled edges where bright arcs appear scalloped or wavy. These features suggest underlying instabilities such as the Rayleigh-Taylor instability, which occurs when a lighter fluid pushes against a heavier one. In this case, hot, low-density ionized gas pushes against cooler, denser molecular gas, producing finger-like protrusions. Over time, these instabilities seed the formation of globules and small clumps within the nebula. The balance of forces in the Lagoon Nebula illustrates a broader principle of astrophysics, the competition between energy injection from stars and the gravitational cohesion of gas clouds. Radiation pressure is one of the main forms of energy injection. Alongside stellar winds and later supernova explosions, it regulates the pace of star formation. If radiation clears gas too efficiently, star formation halts because fuel is removed. If gas remains shielded, star formation continues. The Lagoon Nebula provides an accessible case where radiation pressure is clearly visible in the structures carved into glowing hydrogen. Each arc pillar and rim represents a direct trace of photons moving matter. Uncertainties remain about how far radiation pressure alone can account for the observed morphology. Some astronomers argue that stellar winds play an equal or greater role in shaping cavities, while others emphasize turbulence inherited from the original cloud. Models that combine all three influences reproduce the observations more accurately than any single mechanism. In the Lagoon Nebula, evidence points to radiation pressure as the dominant factor in creating the main cavity, while winds and turbulence refine the details. Measurements of line ratios, gas velocities, and dust distribution help disentangle these contributions, but the complexity of the region ensures that no single explanation is sufficient. Despite these uncertainties, the visual impact of radiation shaping matter is unmistakable. The Lagoon Nebula displays arcs and walls that would not exist without the constant pressure of photons. For observers on Earth, these structures stand as silent records of energetic processes occurring light years away. They demonstrate that even intangible light, when multiplied across countless photons, can move entire clouds of gas and dust. Within the lagoon, nebula radiation pressure serves as a quiet yet powerful sculptor, setting the stage for the creation of new stars and for the eventual dispersal of the nebula itself. Beyond the effects of light itself, the young stars of the Lagoon Nebula launch powerful stellar winds that add another layer of force upon the surrounding gas and dust. A stellar wind is a continuous flow of charged particles such as protons, electrons, and heavier ions expelled from the surface of a star. All stars possess winds, including the Sun, but massive stars produce winds of extraordinary intensity. Their outer layers are so hot and luminous that gravity barely contains them. As radiation accelerates material outward, the result is a supersonic stream that races into the surrounding medium at thousands of kilometers per second. In the Lagoon Nebula, these winds strike against the ambient gas, driving shocks, compressing clouds, and stirring turbulence on vast scales. The interaction between stellar winds and nebula material produces observable signatures. When fast-moving particles collide with denser gas shock fronts form. A shock front is a thin boundary where velocity, pressure, and temperature change abruptly. In such regions, gas is heated to millions of degrees, generating X-ray emission detectable by observatories like Chandra. Within the lagoon, nebula diffuse X-ray emission confirms that shock-heated plasma fills parts of the cavity. These hot regions coexist with cooler ionized hydrogen, demonstrating the variety of physical conditions created by stellar winds. In optical light, the consequences of shocks appear as bright arcs and bow shapes where winds slam into denser clumps. The edges glow as they are ionized, while behind them compressed material may collapse into new stars. One of the key roles of stellar winds is to accelerate the clearing of gas from the central cavity. Whereas radiation pressure alone moves gas gently, winds deliver momentum more directly. When several massive stars launch, winds simultaneously, their combined flows merge into a collective outflow called a cluster wind. This cluster wind sweeps material outward, inflating bubbles that can extend for tens of light years. In the Lagoon Nebula, evidence of such bubbles is visible in the layered structure of gas, with inner shells expanding faster than outer ones. Over time, these bubbles merge with cavities driven by radiation, producing a complex morphology of nested shells and arcs. Winds also produce turbulence. When flows of different speeds collide, they create vortices and eddies that churn the gas. Turbulence breaks smooth structures into fragmented filaments and knots. In the Lagoon Nebula, the irregular appearance of many dust features likely results from this turbulence. Instead of neat, spherical shells, the gas displays clumps, arcs, and chaotic ripples. Spectroscopic measurements reveal velocity dispersions of several kilometers per second across short distances consistent with turbulent motion. Turbulence is significant because it both supports gas against gravitational collapse and paradoxically creates localized compressions that promote star formation. Thus, winds contribute both to the prevention and the triggering of new stellar births. The energy budget of the nebula shows that winds deposit enormous power into the environment. For an O-type star, mass loss through winds may reach 10 millionths of a solar mass per year, with velocities above 1,000 kilometers per second. Multiplying these values yields mechanical luminosities comparable to a significant fraction of the star's radiative output. This means winds cannot be ignored in modelling the nebula's dynamics. In fact, winds are thought to dominate at smaller distances from the star, while radiation pressure becomes more important further out. The interplay between the two creates layered regions, hot shocked wind near the centre, ionized gas surrounding it, and molecular material further out. Observations across wavelengths confirm this stratification in the Lagoon Nebula. Bow shocks around individual stars provide another striking feature. When a star moves through the surrounding gas, its wind collides with the medium, forming a curved shock that wraps around the star like a bow wave in front of a ship. In the Lagoon Nebula, several young massive stars display such bow shocks, visible in infrared as glowing arcs of heated dust. These structures not only mark the presence of winds, but also reveal stellar motions within the cluster. By analysing their orientation, astronomers deduce how stars drift relative to the gas. Such information helps reconstruct the dynamical history of the cluster and the shaping of the nebula. Winds also interact with magnetic fields embedded in the gas. As charged particles stream outward, they follow magnetic field lines, twisting and amplifying them. This coupling alters the distribution of gas, sometimes aligning filaments with field directions. Radiopolarization studies suggest that magnetic fields in the Lagoon Nebula are neither uniform nor negligible. Instead, they weave through the gas-guiding flows and affecting how efficiently winds can disperse material. Strong fields may confine hot plasma, producing localized bubbles, while weaker fields allow freer expansion. This interplay adds another layer of complexity to the already dynamic environment. The chemical consequences of stellar winds are significant as well. Winds carry material from deep layers of stars into the interstellar medium. In massive stars, these winds may include elements such as carbon, nitrogen, and oxygen produced in nuclear reactions. Thus, winds enrich the surrounding nebula with heavy elements before any supernova occurs. Over millions of years, such enrichment contributes to the chemical evolution of the galaxy. In the Lagoon Nebula, enhanced abundances of nitrogen relative to hydrogen have been detected in certain regions, likely reflecting wind contributions from the most massive cluster members. These chemical signatures provide clues about stellar evolution and feedback. Stellar winds also influence the survival of protoplanetary disk around young stars. Disks close to massive stars may be stripped of material by the combined effects of ultraviolet radiation and winds. This process, called photoevaporation, reduces disk lifetimes and may hinder planet formation. In the Lagoon Nebula, infrared observations show disks eroded on sides facing massive stars, forming shapes known as proplids or protoplanetary disk systems. Such structures are more famously observed in the Orion Nebula, but hints of them exist in the Lagoon Nebula as well. Studying these systems reveals how winds and radiation regulate the environments where planets might form, showing the delicate balance required for disks to survive long enough for planets to assemble. The role of winds in triggering star formation remains debated. On one hand, winds compress gas into dense shells that may collapse. On the other hand, the same winds can disperse gas, preventing collapse. Numerical simulations suggest that the outcome depends on the initial conditions. If gas density is above a critical threshold, compression dominates, leading to new stars. If density is lower, dispersal dominates, halting star formation. Observations of the Lagoon Nebula support both outcomes. Along some ridges, young stars clearly form in compressed gas, while in other regions gas is thinned and starless. Thus, winds act as both creators and destroyers, sculpting the nebula in ways that foster and limit stellar birth. Over time, winds significantly alter the fate of the Lagoon Nebula. As massive stars evolve, their winds become even stronger, especially during later stages such as the Wolf-Rayet phase. These winds, carrying enormous momentum and enriched material, will eventually combine with supernova explosions to clear the nebula entirely. For now, the nebula remains intact, glowing under the influence of current winds and radiation. Yet every arc, filament, and cavity bears the imprint of these continuous flows. In the quiet view from Earth, the Lagoon Nebula seems serene, but within it, supersonic winds race and crash endlessly, reshaping the environment. Among the most remarkable regions inside the Lagoon Nebula is a structure often called the hourglass, because of its narrow waist and wider lobes extending outward. This region lies near the bright O-type star Herschel 36, whose immense radiation and stellar wind carve the surrounding gas into a distinctive form. The hourglass shape is not merely a visual impression, but the direct result of physical forces acting on uneven distributions of gas and dust. Close to Herschel, 36 ultraviolet photons ionize hydrogen with great efficiency, clearing channels through the gas. In directions where the surrounding cloud is less dense radiation, and winds carve deeper, creating lobes. In directions where the cloud is thicker, the expansion is slowed, leaving a narrow waist. The combined result resembles two bowls joined at the center, giving the feature its name. The hourglass region illustrates the feedback of massive stars with exceptional clarity. Herschel 36 produces far more energy than the Sun, and its ultraviolet radiation ionizes gas for many light years. As gas is ionized, its temperature rises to thousands of degrees Kelvin, generating internal pressure that drives expansion. The gas expands more easily in less dense directions, creating a symmetry. At the same time, the stellar wind of Herschel 36 collides with surrounding material, forming shock fronts that add to the sculpting. The waist of the hourglass is where denser material resists expansion, while the lobes form where less resistance allows the gas to break through. Over time, this structure evolves as radiation continues to erode the denser waist, and the lobes grow larger. High-resolution imaging from the Hubble Space Telescope reveals intricate details within the hourglass. The central cavity glows intensely in hydrogen emission, with arcs and ridges marking shock fronts. Filaments extend from the waist outward, shaped by both radiation and turbulence. Some of these filaments point directly toward Herschel 36, showing that they are photoevaporation flows, where gas is heated at the surface and streams away into the cavity. Small globules cling to the edges, some harboring young stars detected in infrared surveys. These globules appear as dark knots with bright rims, their shape suggesting that they are slowly being eroded while possibly collapsing inside. Thus, the hourglass region is both destructive and creative, dispersing some material while nurturing new stars in sheltered pockets. Infrared observations provide a complementary view of the hourglass. Dust grains heated by radiation glow at wavelengths invisible to the human eye, outlining structures hidden in optical light. The waist of the hourglass, dark in visible light due to thick dust, glows brightly in infrared, revealing embedded sources. Observations with the Spitzer Space Telescope and more recently with the James Webb Space Telescope confirm the presence of protostars inside the waist. These young objects are still accreting matter from surrounding envelopes, their light trapped by dust. Jets and outflows from some of these protostars emerge into the cavity, detected as narrow emission features. The contrast between the powerful O-type star and fragile newborn stars highlights the variety of stellar stages coexisting within a small region of space. Spectroscopic studies of the hourglass show high-velocity flows of gas. Emission lines from hydrogen and oxygen are broadened and shifted, indicating movement of tens of kilometers per second. These motions reflect the expansion driven by radiation and winds, as well as the outflows from protostars. In some places, red-shifted and blue-shifted components appear side by side, suggesting bipolar outflows piercing the cloud. The waist of the hourglass in particular shows complex kinematics where opposing flows meet. This turbulence may help explain the irregular filamentary appearance of the region. The gas is not moving uniformly, but in overlapping streams, constantly mixing and reshaping. X-ray observations reveal diffuse emission within the hourglass, consistent with shock-heated plasma from the collision of Herschel 36's wind with dense clumps. This high-energy environment can alter the chemistry of the gas, breaking apart molecules and ionizing heavy elements. Chemical traces such as carbon monoxide are depleted near the waist, replaced by atomic and ionized species. At greater distances where shielding is stronger, molecules survive. This chemical stratification mirrors the physical structure, with the most energetic processes nearest the massive star and calmer conditions deeper within sheltered clumps. The hourglass region also demonstrates the role of magnetic fields in shaping nebula structures. Radiopolarization studies suggest that magnetic field lines thread through the waste, possibly guiding flows of gas and influencing the alignment of filaments. Magnetic pressure may help support dense clumps against complete dispersal, allowing protostars to form within them despite the harsh radiation. The alignment of elongated structures with inferred magnetic directions supports this interpretation. If so, the hourglass becomes not just a product of radiation and winds, but also of the unseen architecture of magnetic fields. Astronomers use the hourglass as a case study in feedback mechanisms. Feedback refers to the influence of stars on their birth environment, which in turn regulates further star formation. In the Lagoon Nebula, Herschel 36 provides strong feedback clearing cavities, yet also compressing material into new stars. The hourglass exemplifies this duality. Without massive stars, clouds might collapse into stars, inefficiently forming many low-mass stars but few massive ones. With massive stars, feedback both halts and stimulates star formation, leading to a more complex outcome. Observing how the hourglass evolves helps refine theoretical models of how star clusters regulate themselves. The scale of the hourglass region is vast by human standards, spanning several light years across. Light from the waste takes years to reach the lobes, and the gas moving outward at tens of kilometers per second still requires hundreds of thousands of years to reshape the structure significantly. Yet within astronomical timescales, the hourglass is fleeting. In a few million years, Herschel 36 will end its life in a supernova, blasting away much of the nebula. The hourglass may then vanish entirely, leaving behind the star cluster. For now, however, it stands as one of the most distinctive features within the Lagoon Nebula, visible even in moderate telescopes as a bright knot within the larger glow. From Earth, the hourglass provides a chance to see the interplay of cosmic forces in real time. Its narrow waist and broad lobes are not artistic impressions but the result of quantifiable processes: radiation heating, wind-driven shocks, magnetic support, and gravitational collapse. Each arc and filament tells a story of energy moving through matter. By studying it across multiple wavelengths, astronomers build a layered picture of its dynamics and composition. The hourglass is therefore more than a beautiful sight. It is a natural laboratory where theories of stellar feedback are tested against observation. In the calm voice of the sky, it reminds us that structures arise when forces meet. That form follows the invisible play of energy and matter. Inside the Lagoon Nebula, dense pockets of gas and dust exist where radiation and winds cannot fully penetrate. These compact regions, known as star-forming globules, are the cradles of new stars. A globule is a small, relatively isolated cloud that remains cold and opaque compared to its surroundings. Within such a cloud, gravity can dominate over pressure, leading to collapse. As collapse proceeds, material falls inward, raising the density and temperature at the center. Eventually, a protostar forms, still hidden inside the cocoon of dust. The Lagoon Nebula contains many of these globules scattered along dust lanes, and at the tips of pillars their silhouettes visible as dark patches against glowing emission. They represent the earliest stages of stellar life happening in parallel with the disruptive forces of massive stars nearby. The globules vary in size, but most span less than a light year across. Their masses range from a fraction of the Sun's mass to several tens of solar masses. Inside them, conditions are much colder than in the surrounding cavity. Temperatures drop to about 10 to 20 Kelvin cold enough for molecules such as carbon monoxide, ammonia, and water vapor to exist in abundance. These molecules help radiate heat away, allowing collapse to proceed. Observations at radio wavelengths trace these molecules, revealing velocity gradients that indicate inward motion. In some globules, rotational motion is also detected, suggesting the early formation of disks around forming stars. Infrared imaging provides a key tool for detecting young stars hidden inside globules. At these wavelengths, dust becomes partially transparent, allowing faint light from protostars to escape. Surveys with the Spitzer Space Telescope, and more recently the James Webb Space Telescope, show dozens of point sources embedded in the Lagoon Nebula's globules. Many display infrared excess, a signature of surrounding disks or envelopes. Some show variability over weeks to months, indicating unstable accretion as material falls onto the protostar. These embedded sources confirm that globules are active sites of star formation rather than inert clumps. Jets and outflows often mark the presence of protostars. As matter accretes through a disk onto a central protostar, magnetic fields can channel some of the inflowing material into narrow jets that shoot outward at hundreds of kilometers per second. These jets carve tunnels through the globule, emerging into the surrounding nebula. When the fast-moving gas collides with slower material, it produces shock fronts that glow in emission lines of hydrogen, oxygen, and sulfur. In the Lagoon Nebula, several such jets are observed, some extending for light years. Their narrowness and alignment demonstrate the powerful role of magnetic fields in guiding them. These outflows carry away angular momentum, allowing accretion to continue, and they stir turbulence in the nebula, linking small-scale star formation to the large-scale environment. Not every globule forms a star. Some are eroded before collapse can complete. Radiation from nearby massive stars can strip material from their surfaces, a process called photoevaporation. Over time, an exposed globule may shrink until it disperses completely. Whether a globule survives long enough to form a star depends on its mass density and shielding. Dense, massive globules are more resistant and more likely to collapse, while small, diffuse ones are easily destroyed. The Lagoon Nebula provides examples of both outcomes, some globules with embedded protostars and others fading into the background as they evaporate. This diversity highlights the delicate balance between creation and destruction in star-forming regions. Chemical processes inside globules add further complexity. At low temperatures, molecules freeze onto dust grains, forming icy mantles of water, carbon dioxide, and methanol. These ices serve as sites for chemical reactions that produce more complex molecules, some of which are precursors to organic compounds. When jets or outflows heat the surroundings, these ices evaporate, releasing molecules into the gas phase. Observations of molecular lines in the Lagoon Nebula show evidence of such chemical enrichment. Thus, globules are not only stellar nurseries but also laboratories of chemistry, where the ingredients of future planetary systems begin to assemble. Globules also influence the broader structure of the nebula. Their dense interiors resist the erosive forces of radiation, casting long shadows into the glowing cavity. These shadows appear as dark streaks pointing away from massive stars, outlining the paths of ultraviolet photons. Behind the globules, gas remains shielded, creating cool, elongated tails. This process produces the characteristic cometary shape seen in some regions, where a round head faces the cluster and a tail stretches away. The presence of these cometary globules demonstrates the directional influence of radiation and the survival strategies of dense clumps. Studying globules requires high spatial resolution. With ground-based telescopes blurred by Earth's atmosphere, these structures appear as vague patches. Space telescopes provide the clarity needed to resolve their details. Images from Hubble reveal sharp boundaries, bright rims, and embedded knots. Adaptive optics from ground-based observatories add complementary views, confirming that globules are not uniform but contain substructures. These substructures may fragment further, forming multiple stars within a single globule. Such multiplicity is common in star formation, explaining why many stars exist in binary or multiple systems. The Lagoon Nebula likely contributes numerous such systems to the galaxy. The rate of star formation inside globules remains an area of uncertainty. Astronomers estimate that the efficiency of converting gas into stars is low, perhaps only a few %. Yet because globules are numerous, their combined contribution is significant. In the Lagoon Nebula, the ongoing formation of low-mass stars inside globules complements the presence of massive stars in the cluster. Together they create a full spectrum of stellar masses from red dwarfs to O-type giants. The distribution of these masses, known as the initial mass function, is a key parameter in astrophysics influencing the evolution of galaxies. Globules play a central role in shaping that distribution by producing the numerous low-mass stars that populate the galaxy. Globules in the Lagoon Nebula also provide a link to earlier stages of the cloud. They represent fragments of the original molecular cloud that resisted complete dispersal. Their survival suggests that the parent cloud was clumpy with variations in density across small scales. This clumpiness is typical of turbulent molecular clouds, where random motions create regions of enhanced density. By studying globules, astronomers gain insight into the conditions of the parent cloud and the processes that led to its fragmentation. The Lagoon Nebula thus serves as a natural laboratory for understanding how large clouds break down into star-forming pieces. From Earth, the globules of the Lagoon Nebula are too small to see in detail with the naked eye or small telescopes. They appear only as subtle dark specks within the glowing emission, yet with advanced instruments their importance becomes clear. Each globule is a potential stellar system in the making, a compact site where gravity, radiation, magnetic fields, and chemistry all interact. They embody the balance between destruction by massive stars and creation of new ones. In the quiet view of the Lagoon Nebula, they remind us that even within intense energy fields, small sheltered pockets allow new beginnings. The Lagoon Nebula is not only a place of glowing gas and dark globules, but also a site of powerful flows of material launched from the youngest stars. These flows appear as jets and outflows, narrow streams of gas ejected at high velocity from the immediate surroundings of forming stars. A protostar forms when gravity pulls gas into a dense core, which then accretes material through a rotating disk. As gas spirals inward, angular momentum must be shed, and magnetic fields provide a pathway. The result is a pair of collimated jets launched perpendicular to the disk that blast outward at hundreds of kilometers per second. These jets carve through the surrounding globule, piercing into the ionized cavity of the nebula. In the Lagoon Nebula, jets are observed both as narrow optical features glowing in emission lines and as molecular outflows seen in radio wavelengths. They are among the most dynamic phenomena in the region, linking the intimate process of star birth to the larger environment. Optical images reveal several well-defined jets appearing as thin lines of glowing hydrogen and oxygen stretching for light years. Their brightness comes from shock fronts, where the jet material collides with ambient gas. These shocks heat the gas to thousands of degrees, producing visible emission. The features are known as Herbig-Haro objects, named after the astronomers who first studied them. In the Lagoon Nebula, multiple Herbig-Haro objects have been catalogued, each marking the presence of a hidden protostar within a globule. The jets often appear bipolar, with two opposing streams emanating from a central source. Sometimes one side is brighter than the other, depending on density differences in the surrounding medium. These asymmetries help trace the structure of the cloud around the protostar. Infrared observations add a deeper perspective. At these wavelengths, dust becomes transparent and the embedded protostars themselves can be detected. Many show evidence of disks feeding material inward, consistent with the jet launching model. Infrared images also reveal warm molecular hydrogen emission, tracing outflows broader than the narrow optical jets. These molecular outflows are slower moving at tens of kilometers per second and represent swept-up material rather than the original jet. Together, the fast narrow jet and the slower wide outflow constitute a feedback system. The jet drills a channel while the outflow clears a cavity. In the Lagoon Nebula, such systems are seen emerging from multiple globules, testifying to widespread ongoing star formation. Radio telescopes contribute further by detecting molecules such as carbon monoxide within the outflows. These observations show lobes of gas moving at different velocities, some red-shifted and some blue-shifted relative to the cloud. The red and blue lobes correspond to material moving away and toward the observer, giving a three-dimensional view of the outflow. In the Lagoon Nebula, carbon monoxide mapping reveals dozens of such lobes, confirming that many young stars are actively driving outflows. These data also provide mass estimates showing that significant amounts of gas are being redistributed by protostellar activity. Jets and outflows play an essential role in star formation. Without them, protostars could not efficiently accrete material because excess angular momentum would halt collapse. By ejecting matter along the poles, jets allow disks to funnel gas inward. They also inject energy and momentum into the surrounding cloud, stirring turbulence and shaping the environment. In the Lagoon Nebula, the presence of many jets demonstrates that low-mass star formation is proceeding vigorously, despite the disruptive influence of massive stars. Each jet represents a young star only a few 100,000 years old, still gathering mass but already affecting its neighborhood. The interaction between jets and the larger nebula creates striking structures. Where a jet encounters dense gas, it terminates in a bow shock, a curved front resembling a wave. Bow shocks glow brightly in emission lines, sometimes forming knots that move outward over time. By comparing images taken years apart, astronomers measure proper motions of these knots, confirming velocities of hundreds of kilometers per second. Such measurements in the Lagoon Nebula show jets extending for several light years, with knots advancing steadily. These moving features provide a rare opportunity to witness change in a nebula on human timescales. The energy balance of jets is significant, though smaller than that of massive star winds. Each jet carries mass at rates of millionths to thousandths of a solar mass per year, with kinetic energies comparable to those of small supernova remnants spread over longer timescales. When multiplied by the number of young stars in a cluster, the combined effect of jets contributes substantially to turbulence. In the Lagoon Nebula, jets help maintain the restless state of the gas, preventing collapse in some regions while stimulating it in others. This dual role parallels the larger-scale effects of radiation and winds, showing that feedback occurs across all mass scales of stars. Observations of jets also provide clues to the magnetic environment. The collimation of jets into narrow beams requires strong magnetic fields threading the disk and protostar. These fields guide material along lines of force, accelerating it outward. Variability in jet brightness often reflects changes in accretion rate, which in turn alter the magnetic launching conditions. In some cases, jets appear twisted or show wiggles, possibly indicating precession of the disk or magnetic instabilities. Such features have been documented in the Lagoon Nebula, where certain jets curve or branch. Studying them helps refine theories of magnetohydrodynamic launching, one of the key unsolved problems in star formation physics. Jets and outflows also influence the chemical state of the nebula. As shock fronts propagate, they heat and compress gas-driving reactions that produce molecules otherwise rare in cold conditions. For example, shocks can liberate water vapor from icy grain mantles and create complex organic molecules. Observations of shocked regions in the Lagoon Nebula indeed show enhanced molecular abundances. These processes enrich the nebula, seeding it with ingredients that may later become part of planetary systems. In this way, jets contribute to the chemical as well as the physical evolution of the region. One challenge in studying jets is distinguishing them from other filamentary structures. The Lagoon Nebula contains many linear features produced by radiation or winds. To confirm a jet, astronomers look for high-velocity emission bipolar symmetry and association with a young star. When these criteria are met, the feature can be confidently identified as a jet. In the Lagoon Nebula, dozens of such identifications have been made, making it one of the richest fields for studying protostellar outflows. The combination of optical, infrared, and radio data provides a complete view of their properties. From the perspective of Earth, jets appear as delicate threads within the glowing expanse, almost lost among the brighter emission. Yet each marks a vigorous process, a star drawing material inward, while expelling part of it outward, balancing the equations of momentum and energy. They are reminders that even the smallest stars shape their environment. In the Lagoon Nebula, jets and outflows create a fine network of activity woven through the larger drama of massive star feedback. Together they illustrate how star formation is not an isolated event, but a continuous interaction between newborn stars and the cloud that nurtures them. When astronomers study the Lagoon Nebula, they do not rely on a single window of light. Instead, they observe the nebula across multiple wavelengths, each revealing a different layer of structure and physical process. In visible light, the nebula shines most prominently in the red glow of ionized hydrogen, along with contributions from oxygen and sulfur. This view emphasizes the bright emission region's dust lanes and striking hourglass cavity near Herschel 36. But visible light is only one piece of the spectrum. Because dust absorbs and scatters shorter wavelengths, much of the action within the nebula remains hidden from direct optical view. To gain a full understanding, astronomers turn to infrared, radio, and X-ray observations, building a composite picture that goes far beyond what the human eye can see. Infrared observations are particularly valuable for probing dust and young stars. At wavelengths longer than visible light, dust becomes transparent, allowing embedded structures to emerge. Surveys with the Spitzer Space Telescope first revealed a wealth of young stellar objects inside the Lagoon Nebula, identified by their strong infrared excess from surrounding disks and envelopes. Later, the James Webb Space Telescope provided even sharper detail, showing protostars in the hourglass region, and globules, each with characteristic outflows and cavities. Infrared images also highlight warm dust grains heated by ultraviolet radiation, glowing at tens to hundreds of Kelvin. These emissions trace the distribution of material otherwise invisible in optical images. By mapping the nebula in infrared, astronomers identify the hidden population of stars and measure the properties of the cold clouds from which they form. Radio and submillimeter observations add another essential perspective. At these wavelengths, molecules such as carbon monoxide, ammonia, and formaldehyde emit characteristic lines that allow astronomers to map cold gas. The Lagoon Nebula contains extended molecular clouds, remnants of the parent cloud that gave birth to the cluster. Radio telescopes such as ALMA and single-dish observatories like the Atacama Pathfinder experiment detect these emissions, showing how gas flows fragments and condenses into star-forming clumps. Radio mapping reveals velocity structures, with some regions collapsing inward and others expanding under feedback. This dynamic interplay demonstrates that the nebula is not static, but continually evolving. Submillimeter continuum emission also traces dust, directly providing mass estimates for globules and filaments. Together, these radio data give the clearest picture of where star formation may continue in the future. X-ray observations reveal the highest energy processes. The Chandra X-ray Observatory has imaged the Lagoon Nebula, detecting both point sources and diffuse emission. The point sources correspond to young stars which are highly magnetically active and produce powerful flares. These flares accelerate particles and emit X-rays far more intense than those from older stars. The diffuse emission arises from hot plasma at millions of degrees, generated when stellar winds collide and shock the surrounding gas. X-rays penetrate dust, offering a view into regions opaque in other wavelengths. In the Lagoon Nebula, Chandra observations confirm that feedback from massive stars heats large volumes of gas, contributing to turbulence and altering chemistry. X-rays also influence disk survival as they ionize material and drive evaporation. By combining these different windows, astronomers construct a layered model of the Lagoon Nebula. In the optical, they see the glowing ionized shell. In the infrared, they uncover embedded stars and warm dust. In the radio, they trace the cold molecular gas-feeding star formation. In X-rays, they detect the hot plasma energized by winds and shocks. Each wavelength highlights a distinct regime of temperature density, and process from a few tens of Kelvin in cold clumps to millions of Kelvin in shocked bubbles. No single view suffices, but together they provide a coherent narrative of how energy flows through the nebula. Multi-wavelength studies also resolve uncertainties about distance and structure. For example, parallax measurements from the Gaia mission, combined with infrared identification of cluster members, refine the distance estimate to about 4,000 to 5,000 light-years. Radio observations confirm that the molecular gas shares consistent velocities with this distance. Meanwhile, X-ray detections of young stars confirm that they belong to the cluster rather than being foreground or background objects. By aligning all these datasets, astronomers ensure that they are studying a physically coherent system rather than a chance alignment of unrelated objects. The multi-wavelength approach also reveals time-dependent processes. Variability in X-rays traces magnetic flares on young stars. Changes in infrared brightness signal episodic accretion events as protostars gather matter from their disks. Jets observed in optical and infrared show knots moving outward over years. By combining these time-variable signals across the spectrum, astronomers can track how individual stars evolve within the larger context of the nebula. The Lagoon Nebula thus becomes not just a static picture, but a dynamic movie with each wavelength, providing a different frame. One striking example of the power of multi-wavelength study is the hourglass region. In visible light, it appears as a bright glowing cavity. In infrared, it reveals embedded protostars and dusty ridges. In X-rays, it glows faintly with hot plasma. In radio, molecular traces show inflows and outflows shaping the waste. Only by combining all these views can the hourglass be understood as a complex interaction of massive star feedback and ongoing star formation. Without this layered approach, the role of Herschel 36 and the survival of nearby protostars would remain obscure. Another example lies in the dust lanes crossing the nebula. In visible light, they appear as dark streaks. In infrared, they glow faintly as warm dust. In radio, they shine brightly in molecular lines, revealing dense cold reservoirs. The same feature seen differently tells multiple stories: obscuration in optical emission in infrared and fuel for star formation in radio. These complementary views highlight the necessity of looking across the spectrum to avoid misleading impressions. The Lagoon Nebula demonstrates vividly that appearances depend on wavelength. Multi-wavelength observations also connect the Lagoon Nebula to broader astrophysical questions. How does feedback regulate star formation efficiency? How do disks survive in harsh environments? How are molecules and dust distributed across turbulent clouds? Each of these questions requires data from different regimes. For example, feedback is traced by X-rays and optical shocks, disk survival by infrared excess, and molecular distribution by radio mapping. The Lagoon Nebula, because of its proximity and brightness, serves as a benchmark for addressing these questions. Lessons learned here can be applied to more distant star-forming galaxies, where such detail cannot be observed directly. For observers on Earth, the beauty of multi-wavelength images lies not only in science but in aesthetics. Composite images combining optical infrared and X-ray data produce richly colored portraits where each hue corresponds to a physical process. The Lagoon Nebula, when shown in these composites, displays a tapestry of red, green and blue, each representing hydrogen, oxygen dust or hot plasma. These images, while scientifically calibrated, also provide a striking reminder that nature expresses itself differently depending on how it is observed. The nebula exists as one entity, but our understanding grows only when all its voices are heard. Ultimately, the multi-wavelength view underscores the complexity of the Lagoon Nebula. It is not a uniform cloud, but a layered structure where temperatures, densities, and processes vary dramatically from one place to another. Visible light alone shows beauty but hides much. Infrared, radio, and X-rays add depth, uncovering the hidden, the cold, and the hot. Together, they reveal a complete ecosystem of star formation and feedback. In the calm study of each wavelength, the nebula discloses its secrets, slowly showing that science progresses most when many perspectives are joined. The Lagoon Nebula is a place where gravity radiation and winds interact, but another player in the shaping of its structures is the magnetic field that threads through the gas and dust. Magnetic fields are invisible lines of force created by moving charges. In interstellar space, they are weak compared to gravity or thermal pressure, but because gas in nebula is ionized, even a weak magnetic field can guide motion over large scales. In the lagoon, nebula evidence shows that magnetic fields influence the alignment of filaments, regulate the collapse of globules, and help collimate the jets from young stars. By studying the magnetic structure, astronomers gain insight into how star-forming regions achieve their complex appearances. Magnetic fields in the interstellar medium are detected through several techniques. One common method is polarization of starlight. Dust grains align their long axes perpendicular to the magnetic field, so light passing through becomes polarized in a direction that reveals the field orientation. Observations of stars behind the Lagoon Nebula show consistent polarization patterns, indicating that fields run across certain filaments. Another method is Zeeman splitting, where magnetic fields slightly shift the energy levels of atoms and molecules, splitting their spectral lines. Radio observations of molecules such as hydroxyl in the Lagoon Nebula show such splitting, giving direct estimates of field strength. Typical values are a few tens of microgauss small in absolute terms, but influential when integrated over parsec scales. The orientation of filaments in the Lagoon Nebula often matches the direction of magnetic fields inferred from polarization studies. This suggests that magnetic fields guide the flow of gas resisting compression across the field lines but allowing easier motion along them. As a result, filaments become elongated in directions parallel to the field. This alignment cannot be explained solely by turbulence or winds. Instead, it reflects the underlying structure imposed by magnetic pressure. In some regions, filaments curve toward massive stars, showing that radiation and winds bend them, but the underlying orientation still traces magnetic lines. This combination of shaping forces produces the intricate web of structures visible in high-resolution images. Magnetic fields also play a crucial role in the survival of globules. In dense clumps, gravity pulls gas inward, while thermal and turbulent pressures push outward. Magnetic pressure adds another source of support. If the field is strong enough, it can delay or even prevent collapse. But as gas accumulates and becomes denser, the magnetic field lines become squeezed, increasing resistance. Eventually, if gravity is overwhelming, collapse proceeds. This process, called ambipolar diffusion, occurs when neutral gas drifts slowly through ionized components tied to field lines. In the Lagoon Nebula, globules showing signs of star formation may be those where ambipolar diffusion has allowed collapse despite magnetic support. Others still intact but without stars may remain magnetically stabilized for longer periods. The launching of jets from protostars provides another example of magnetic influence. Jets are believed to be driven by magnetohydrodynamic processes, where magnetic fields anchored in the disk and star accelerate plasma outward along lines of force. Without magnetic collimation, jets would disperse quickly and lose their narrow form. Observations of jets in the Lagoon Nebula, some extending for light years while remaining only fractions of a light year wide, demonstrate effective collimation. Theoretical models reproduce this by invoking magnetic fields threading the disk, twisted by rotation, into helical shapes that sling material outward. Thus, the very presence of visible jets serves as evidence that magnetic fields are active on small scales. Magnetic fields also interact with stellar winds. Charged particles in winds spiral along field lines, amplifying turbulence and producing irregularities in shock fronts. This may explain why some arcs in the Lagoon Nebula appear rippled rather than smooth. Instabilities such as the Kelvin-Helmholtz instability, driven by velocity differences, are modified by magnetic tension that resist bending. The result is a complex interplay between fluid motion and magnetic structure. Numerical simulations, including magnetic fields, reproduce more realistic morphologies than models without them, underscoring their importance. On larger scales, the Lagoon Nebula is embedded in the galactic magnetic field that permeates the disk of the Milky Way. This field provides a background orientation that influences how clouds form and evolve. The Lagoon Nebula's filaments show partial alignment with this galactic field, suggesting that its parent molecular cloud inherited the orientation before stars formed. As collapse progressed, local conditions modified the field, twisting it around cavities and bending it along expanding shells. The present pattern is therefore a combination of inherited structure and local feedback. By studying the Lagoon Nebula in comparison with other star-forming regions, astronomers test theories of how galactic fields regulate star formation on both local and global scales. Observations of polarized emission in the far infrared provide additional information. Dust grains emit polarized light as they radiate heat, and the polarization reveals magnetic orientation. The Planck satellite mapped such emission across the sky, including the region of the Lagoon Nebula. These maps show that fields are coherent over many parsecs, not random or chaotic. In some areas, polarization vectors bend around cavities, showing that feedback from massive stars has distorted the field. This bending indicates that magnetic energy is not dominant but is still significant enough to resist complete disruption. The field acts as a memory of past events, recording the flow of gas and the influence of stars. The relative strength of magnetic pressure compared to other forces is often described by a dimensionless number called the plasma beta, which is the ratio of gas pressure to magnetic pressure. In regions where beta is greater than one, gas motions dominate and fields are dragged along. In regions where beta is less than one, fields control motion, and gas flows along them. Measurements in the Lagoon Nebula suggest that different regions fall into different regimes. In dense filaments, beta is low, so magnetic fields constrain collapse. In the hot cavity, beta is high, so gas expands freely, dragging fields outward. This spatial variation explains why some structures are strongly aligned while others appear chaotic. Understanding magnetic fields is essential for addressing the efficiency of star formation. If fields are strong, they delay collapse, lowering efficiency. If they are weak, collapse proceeds rapidly, producing many stars in a burst. The Lagoon Nebula, with its mixture of ongoing star formation and strong feedback, offers an intermediate case. Fields appear strong enough to regulate collapse, but not to halt it. The result is a balanced process where stars form over millions of years, rather than in a single episode. This measured pace may explain why clusters like NGC 6530 contain both very young and slightly older stars. Magnetic fields also contribute to cosmic ray propagation. Cosmic rays are high-energy particles that travel through the galaxy, guided by magnetic fields. In star-forming regions, supernova and winds produce cosmic rays, which then diffuse along field lines. The Lagoon Nebula, still too young for many supernovae nonetheless, contains winds and shocks that accelerate particles. Magnetic fields trap some of these particles, influencing ionization and chemistry. Though difficult to measure directly, these processes highlight yet another role of magnetism in shaping the astrophysical environment. From Earth, the influence of magnetic fields in the Lagoon Nebula is invisible to the eye. Yet through careful measurement of polarization and spectral lines, their presence becomes clear. They weave through the gas like unseen threads, guiding, resisting, and recording motion. They ensure that collapse occurs unevenly, that jets remain narrow, and that filaments align in preferred directions. The Lagoon Nebula thus embodies not only the visible play of light and shadow, but also the hidden architecture of magnetism. In the slow unfolding of its patterns, the signature of magnetic fields remains etched, subtle but profound. The Lagoon Nebula is not a static picture, but a place of motion where gas flows collides and stirs under the influence of gravity, winds, and radiation. Measurements of these motions reveal turbulence, expansion, and shock waves that together shape the cloud. Astronomers detect such movements through spectroscopy, examining the Doppler shifts of emission and absorption lines from hydrogen, oxygen, carbon monoxide, and other atoms or molecules. A red shift indicates gas moving away along the line of sight, while a blue shift indicates gas approaching. By mapping these shifts across the nebula, scientists build velocity maps showing patterns of motion that are invisible to the eye. These maps demonstrate that the Lagoon Nebula is restless, with streams and eddies in constant flux. One of the most prominent motions is the expansion of the central cavity around the cluster, NGC 6530. The ionized gas inside is hotter and therefore at higher pressure than the cooler molecular gas outside. Pressure differences drive outward flows at several kilometers per second. Over tens of thousands of years, this expansion carries gas outward by many light years. Spectra of hydrogen emission lines confirm this expansion, showing systematic velocity shifts consistent with a bubble growing from the cluster outward. Superimposed on this global expansion are localized flows where winds and jets punch through, creating faster-moving features. Turbulence adds further complexity. Rather than smooth expansion, the gas shows velocity dispersions, meaning that at any given point gas parcels move at different speeds and directions. These dispersions range from a few to several kilometers per second, depending on location. Turbulence arises naturally when winds collide, when radiation pushes unevenly, and when gravity draws clumps together. It fragments the gas into filaments and knots, preventing uniform collapse. At the same time, turbulence compresses gas, locally seeding new star formation. This dual role mirrors the balance seen throughout the nebula. Forces that disrupt also create. Shock waves are another key element of motion. When a supersonic wind or jet collides with slower gas, a shock front forms. In shocks, energy is suddenly converted into heat, raising gas temperatures to thousands or even millions of degrees. These regions emit strongly in specific lines, making them visible markers of dynamical activity. In the Lagoon Nebula, shocks are observed at the edges of cavities, along bow fronts around globules, and in Herbig-Haro objects from protostars. Some shocks produce X-ray emission evidence of very hot plasma. Others produce optical arcs of glowing hydrogen. Each shock is a record of a past collision between flows of different speeds. The kinematics of the Lagoon Nebula are not uniform across the region. Near Herschel, 36 velocities are highest, with gas streaming outward rapidly due to the intense wind and radiation. In the hourglass region, multiple flows intersect, producing turbulent mixing layers where velocity changes abruptly. In dust lanes, motions are slower, with some parts even showing signs of infall rather than expansion. These differences reflect the balance of forces at each location. High-resolution velocity maps reveal swirling eddies, where streams of gas curl around dense clumps, creating vortices on scales of fractions of a light year. Over time, these vortices may dissipate or feed into larger flows, but for now they contribute to the complexity of motion. The role of gravity is not absent from these dynamics. While winds and radiation push outward, gravity from the cluster and from dense clumps pulls inward. In some globules, spectral lines show infall signatures with asymmetric profiles, indicating gas collapsing toward a center. Such infall is the hallmark of star formation, where gravity overcomes turbulence. Thus, the Lagoon Nebula contains both outward expansion from massive stars and inward collapse in smaller clumps occurring simultaneously. This coexistence illustrates the multi-scale nature of nebula dynamics, with different regimes of motion overlapping in the same environment. The energy injected into the nebula maintains its turbulence. Without continual input, turbulence would decay over timescales of a few million years. The presence of O-type stars ensures constant energy supply through winds, radiation, and eventually supernovae. This injection sustains the restless state, preventing the nebula from settling into a simple equilibrium. For astronomers, this is important because turbulence regulates star formation efficiency. If turbulence is too strong, collapse is suppressed. If turbulence decays, collapse accelerates. The Lagoon Nebula, with its moderate turbulence levels, shows star formation continuing, but not at maximum efficiency, consistent with observed populations of stars. Chemical traces provide further details of motion. Molecules like carbon monoxide emit lines that are sensitive to density and velocity. By examining line widths and shifts, astronomers measure turbulence inside cold clumps. In the Lagoon Nebula, these line widths are broader than expected from thermal motion, alone confirming that non-thermal turbulence dominates. Some clumps show velocity gradients suggesting rotation or shear. Such gradients may lead to disk formation around young stars. Other clumps show multiple velocity components indicating overlapping flows or collisions. These data paint a picture of a cloud in which gas is not at rest, but constantly moving, colliding and reorganizing. Uncertainties remain in interpreting these motions. Projection effects complicate analysis because velocity measurements capture only the component along the line of sight. Flows moving perpendicular remain hidden, leading to ambiguities in three-dimensional structure. Astronomers combine velocity maps with morphological clues from images to reconstruct motion in full space. Numerical simulations help by modeling how winds, radiation, and gravity interact. Comparing simulations with observations allows inference of likely flow patterns. For the Lagoon Nebula, simulations reproduce expanding bubbles, turbulent filaments, and jets consistent with what is observed, giving confidence that the main processes are understood. The interplay of turbulence and collapse raises questions about the future of the nebula. If turbulence continues, it may disperse much of the gas before it can collapse into stars, lowering the overall star formation efficiency. If turbulence decays or is locally reduced, pockets of gas may collapse more rapidly, forming clusters of low-mass stars. Observing current motions provides a snapshot of this competition. The Lagoon Nebula shows both dispersal where gas is moving outward and concentration where clumps are infalling. The eventual outcome will depend on which process dominates over the next few million years. From Earth, the restless motion of the Lagoon Nebula is invisible to the naked eye. The nebula appears as a faint glow in Sagittarius, seemingly quiet. Only through spectroscopy and imaging do the hidden motions reveal themselves: expansions, shocks, turbulence, and infall, all playing out on scales of light years. These motions are slow compared to human experience, yet immense in their reach. Over millions of years, they will reshape the nebula, dispersing some regions while forming stars in others. For now, they remind us that even in apparent stillness, the universe is never static, but always in motion, guided by the fundamental forces of physics. The Lagoon Nebula is more than a field of glowing gas. It is also a repository of molecules and dust grains that trace the colder and denser regions hidden from optical view. These traces provide vital clues about the physical conditions inside the cloud and the processes that give rise to new stars. At low temperatures, atoms combine into simple molecules such as molecular hydrogen, carbon monoxide, ammonia, and formaldehyde. Because molecular hydrogen is difficult to detect directly, astronomers rely on other species, particularly carbon monoxide, as a proxy. Radio telescopes measure the emission of carbon monoxide lines at millimeter wavelengths, mapping where the coldest reservoirs of gas reside. In the Lagoon Nebula, such maps reveal a patchwork of dense clumps and extended filaments, often aligned with the dust lanes seen in optical images. These regions are the raw material from which stars form. Carbon monoxide is not the only tracer. Molecules such as carbon monosulfide, hydrogen cyanide, and ammonia emit at characteristic frequencies that probe different densities and temperatures. For example, ammonia is sensitive to gas near 20 Kelvin, allowing precise temperature measurements. Observations of the Lagoon Nebula with facilities like the Green Bank Telescope and ALMA have detected these molecules, showing that the coldest clumps maintain temperatures of only a few tens of Kelvin despite the intense radiation nearby. This survival occurs because dense gas self-shields, absorbing ultraviolet light in its outer layers and protecting the core. These shielded cores become sites of star formation, insulated from the destructive forces outside. Dust grains provide another tracer of cold material. Composed of silicates, carbon compounds, and ices, dust grains emit faint thermal radiation at infrared and submillimeter wavelengths. By measuring this emission, astronomers estimate dust mass and infer total gas mass, since gas and dust are mixed in fairly constant proportions. Observations with the Herschel Space Observatory showed bright far-infrared emission along the dust lanes of the Lagoon Nebula corresponding to large quantities of cold material. From these data, scientists estimate that the nebula contains tens of thousands of solar masses of gas and dust, sufficient to form many new stars. The distribution of this mass is uneven, concentrated in clumps that vary in size and density. The chemical richness of the Lagoon Nebula includes complex molecules. In some clumps, methanol and other organic molecules have been detected. These species form on dust-grained surfaces where atoms stick and react under cold conditions. When jets or shocks heat the clumps, the ices evaporate, releasing molecules into the gas phase. This process creates chemical diversity that enriches the surrounding medium. Though the Lagoon Nebula is not as chemically rich as some older star-forming regions, its detection of organics shows that even in a relatively young environment, the seeds of chemical complexity are present. Such molecules may later become part of protoplanetary disks, linking nebular chemistry to planetary formation. The abundance of different molecules provides clues to the evolutionary state of clumps. In the youngest, coldest clumps, molecules such as carbon monoxide dominate while more complex organics remain frozen. In clumps with embedded protostars heating from the young star drives, evaporation producing richer spectra. By comparing molecular line strengths, astronomers classify clumps into evolutionary stages. In the Lagoon Nebula, this method reveals a spectrum of activity, with some clumps still starless and others already harbouring young stars. This range of conditions illustrates that star formation proceeds over extended timescales rather than in a single burst. Chemical traces also reveal motion. Because molecular lines shift with velocity, they provide detailed maps of gas dynamics. Observations of carbon monoxide in the Lagoon Nebula show expanding shells near massive stars, collapsing motions in dense globules, and turbulent flows throughout. Some clumps display clear signs of infall with asymmetric line profiles, indicating gas moving inward faster than outward. Others show outflow signatures with broad wings caused by jets pushing material outward. These velocity structures confirm that molecules trace both the quiet reservoirs and the active processes of star formation. Dust grains influence not only chemistry, but also radiation. By absorbing ultraviolet and visible light, dust grains heat up and re-radiate in the infrared. This process both cools the gas and redistributes energy. The presence of dust explains why regions behind lanes appear dark in optical light, but bright in infrared. Dust also polarizes light, aligning with magnetic fields, which allows astronomers to infer the hidden structure of the field. In the Lagoon Nebula, far-infrared polarization maps show fields threading the dust lanes, reinforcing the connection between magnetism and structure. The distribution of dust affects the visibility of stars. Extinction. The dimming of starlight by dust varies across the nebula. Some stars in the cluster appear bright and unobscured, while others are reddened or invisible in optical light. Correcting for extinction requires careful modelling of dust properties, including grain size and composition. In the Lagoon Nebula, extinction measurements suggest a mixture of grain sizes, some larger than typical interstellar grains. Such growth may occur within dense clumps where grains stick together, forming the precursors of planetesimals. Thus, dust in the nebula is not only a tracer, but also a participant in the early steps of planet formation. Another chemical tracer comes from ionized species. In the ionized regions of the nebula, lines of oxygen, nitrogen, and sulfur reveal electron densities and temperatures. These diagnostics confirm that gas in the cavity reaches several thousand degrees Kelvin. In combination with molecular data, they show the transition from hot ionized plasma in the cavity to warm atomic gas in the photodissociation regions to cold molecular cores deep inside clumps. This layered structure, called a stratified medium, is typical of star-forming regions. The Lagoon Nebula offers one of the clearest local examples, allowing detailed study of how radiation transforms chemistry across boundaries. Uncertainties remain in interpreting molecular and dust traces. Beam dilution, where telescopes average signals over large areas, can mask small-scale variations. Chemical abundances depend on models of excitation and depletion, which may differ among environments. For the Lagoon Nebula, observations from multiple instruments and wavelengths help reduce these uncertainties. By combining data from Alma Herschel and ground-based radio arrays, astronomers build consistent models of gas density, temperature, and composition. These models match the observed star formation rate, supporting the picture that dense molecular clumps are the key sites of activity. From Earth, the chemical richness of the Lagoon Nebula is invisible to the eye, which perceives only the red glow of hydrogen. Yet through radio and infrared instruments the hidden layers emerge. Molecules trace cold reservoirs, dust grains reveal masses and fields, and ions mark hot plasma. Together they show that the nebula is not a uniform cloud, but a chemically diverse environment, where physical and chemical processes intertwine. The Lagoon Nebula thus stands as both a stellar nursery and a chemical workshop, forging the conditions for stars and potentially the ingredients of planets. One of the enduring challenges in the study of the Lagoon Nebula is determining its true distance scale and age. These parameters are fundamental because they underlie every calculation of luminosity size and mass. If the distance is uncertain, so too are the derived properties of its stars and clouds. The Lagoon Nebula is located in the direction of the Sagittarius arm of the Milky Way, a region crowded with stars and dust. This makes accurate measurement difficult because foreground and background stars overlap along the line of sight. Over decades, astronomers have applied multiple methods, each refining the estimates, but leaving a margin of uncertainty that persists today. Early attempts relied on spectroscopic parallax, which involves measuring the spectra of bright stars in the cluster and comparing their observed brightness to the expected luminosity for their type. This method suggested a distance of around 5,000 light-years. Later radio measurements of molecular lines offered similar numbers, but with large uncertainties due to assumptions about galactic rotation. More recently, the Gaia Space Observatory provided precise parallax measurements for individual stars within NGC 6530. These data indicate a distance closer to 4,000 to 4,300 light-years. This represents an improvement, but still carries uncertainties as dust extinction and crowding complicate the analysis. The current consensus lies between 4,000 and 5,000 light-years, with ongoing work to narrow the range further. The scale of the Lagoon Nebula depends directly on the distance. At 4,000 light-years, its apparent size of about 1 degree on the sky corresponds to a physical span of about 50 to 60 light-years across. This makes it a giant molecular cloud complex comparable to the Orion Nebula, but located further away. Its central cavity measures several tens of light-years, while filaments and dust lanes extend even further. Knowing this scale allows astronomers to estimate masses of clumps, sizes of outflows, and luminosities of stars. A difference of even a few hundred light-years in distance translates into significant changes in these derived values, so accurate measurement remains a priority. The age of the nebula and its cluster is another area of uncertainty. The cluster NGC 6530 contains stars at different stages of evolution. Massive O-type stars such as Herschel 36 are only a few million years old at most, because such stars cannot live longer than that before exhausting their fuel. Lower mass stars in the cluster appear to be slightly older, perhaps up to 5 million years based on their positions in the Hertzsprung-Russell diagram. Some embedded protostars are even younger still, forming within globules. This spread in ages suggests that star formation in the Lagoon Nebula has been ongoing for several million years and continues today. Pinpointing the start of this process is difficult because molecular clouds evolve gradually rather than in sudden bursts. Estimates generally place the onset of star formation at around 2 to 5 million years ago. Age estimates for individual features also vary. The hourglass region around Herschel 36 likely formed within the past few 100,000 years as the star's radiation and winds carved the cavity. Jets and Herbig-Haro objects trace events only tens of thousands of years old. Globules and disks represent even more recent activity ongoing at present. Thus, while the overall nebula is a few million years old within it, lie structures spanning a broad range of ages from newborn protostars to nearly mature cluster members. This mixture complicates efforts to assign a single age but provides a valuable record of sequential star formation. Another uncertainty arises in determining the total mass of the nebula. Estimates based on molecular emission suggest tens of thousands of solar masses, but these depend on conversion factors from carbon monoxide brightness to hydrogen mass. Dust emission provides complementary estimates, but requires assumptions about grain properties. Different methods yield results that agree within factors of 2 or 3, but not more precisely. The uncertainty in mass feeds back into uncertainty in star formation efficiency, which is the ratio of stellar mass to gas mass. For the Lagoon Nebula, efficiency appears to be a few % consistent with other giant molecular clouds, but exact numbers remain debated. The geometry of the nebula adds complexity. The Lagoon Nebula is not a flat sheet but a three-dimensional structure with overlapping layers along the line of sight. Some dust lanes may be foreground features while others lie embedded within the emission. Determining the relative placement of these structures is challenging without three-dimensional velocity information. Spectroscopy provides some clues showing which regions are moving toward or away, but full reconstructions remain model-dependent. As a result, images of the nebula, while beautiful, can give a misleading impression of depth. Astronomers must rely on careful modelling to interpret what features lie in front, behind, or inside the glowing gas. Uncertainties also extend to the exact role of feedback in triggering star formation. While observations show young stars along bright rims and compressed ridges, it is difficult to prove causation. Did radiation and winds from massive stars trigger collapse, or did collapse begin independently before feedback arrived? Time sequencing is hard to establish because stars form over hundreds of thousands of years, while gas motions unfold over similar timescales. Models suggest that both processes occur. Some stars form spontaneously, while others are induced by compression. In the Lagoon Nebula, evidence for both exists, leaving open questions about relative contributions. Distance uncertainties impact not only physical scales, but also interpretations of brightness and energy. For example, the luminosity of Herschel. 36 depends on distance squared. At 4,000 light-years, its luminosity is hundreds of thousands of times that of the Sun. At 5,000 light-years, it would be significantly higher. Such differences affect estimates of how much radiation drives the nebula's evolution. Likewise, the size and mass of the cluster depend on distance. This illustrates why narrowing the distance range is critical for precise modelling. Despite these uncertainties, astronomers have converged on a coherent picture. The Lagoon Nebula is a massive, relatively nearby star-forming region, spanning about 50 light-years with an age of a few million years and an ongoing process of star birth. Its most massive stars dominate its appearance, while numerous lower-mass stars and protostars populate its globules and filaments. The uncertainties that remain are not obstacles but opportunities. Each refinement in distance, scale, or age improves our understanding not only of this nebula, but of star formation in general. From Earth, the Lagoon Nebula is visible to the naked eye under dark skies, appearing as a faint smudge in Sagittarius. Telescopes reveal its structure, but measurements of distance and age require far more subtle techniques. Through decades of effort, astronomers have narrowed uncertainties but acknowledged the limits of current methods. The Lagoon Nebula stands as a reminder that even nearby cosmic structures hold mysteries, and that progress comes step by step through careful observation and refinement. Its uncertain distance and age do not diminish its importance, but rather highlight the ongoing nature of scientific inquiry, where each answer opens new questions. The Lagoon Nebula has been studied for centuries through ground-based telescopes, but the true richness of its structure only became clear with modern observatories spanning the electromagnetic spectrum. Each instrument brings unique capabilities, and together they construct a layered understanding of this star-forming region. Among the most influential are optical telescopes, such as the Hubble Space Telescope infrared instruments, like the Spitzer Space Telescope and the James Webb Space Telescope Radio, and sub-millimeter facilities such as ALMA and high-energy observatories like Chandra. Each reveals different processes from glowing plasma to hidden protostars, and their combined view has transformed the Lagoon Nebula from a bright patch in the sky into a detailed case study of astrophysical feedback and star formation. The Hubble Space Telescope provided some of the most detailed optical images of the Lagoon Nebula, including close-up views of the hourglass region. Its high-resolution resolved filaments, globules and jets showing that features once seen as blurry patches are actually intricate structures. Hubble's narrow-band imaging of hydrogen, oxygen and sulfur lines allowed astronomers to map ionization fronts and shock waves. These data confirmed the role of Herschel-36 in carving the hourglass cavity and identified embedded protostars along bright rims. The images also served as a visual benchmark widely shared with the public, demonstrating the scientific and aesthetic power of space-based imaging. The Spitzer Space Telescope extended the view into the infrared, where dust becomes transparent and warm grains glow. Spitzer revealed hundreds of young stellar objects previously unseen in optical light, each identified by its infrared excess. The observations showed that the Lagoon Nebula is far richer in star formation than visible images suggest, with stars forming throughout its dust lanes and globules. Spitzer also mapped polycyclic aromatic hydrocarbons molecules excited by ultraviolet radiation that glow in mid-infrared wavelengths. These traces outlined photodissociation regions, where ionized gas meets molecular clouds. The resulting maps highlighted the layered transition zones that mark the nebula's complex energy balance. The James Webb Space Telescope has added even greater clarity in the infrared. Its instruments provide resolution comparable to Hubble, but at longer wavelengths, penetrating dust and revealing protostars with unprecedented detail. Observations of the hourglass region with Webb show disks around young stars, outflows carving narrow cavities, and knots of dust shielding star formation from radiation. Spectroscopic data identify molecules such as carbon dioxide and water vapor in these environments, providing chemical fingerprints of early planetary building blocks. The Lagoon Nebula thus becomes not only a site of star formation, but also a place where the precursors of planetary systems can be studied. Radio and submillimeter observatories provide the complementary view of cold gas. The Atacama Large Millimeter Array ALMA offers the highest resolution in this regime, mapping carbon monoxide and other molecules across the nebula. ALMA data reveal rotating cores, inflowing material and broad molecular outflows, tracing the earlier steps of star formation. Single-dish telescopes like APEX and the James Clerk Maxwell Telescope extend coverage to larger scales, showing the broader molecular cloud that feeds the Lagoon Nebula. These observations quantify the gas mass density distribution and turbulence, providing the context in which star formation proceeds. They also identify chemical variations such as regions enriched in methanol or sulfur-bearing species indicating active chemistry in shocked gas. High-energy observations from the Chandra X-ray Observatory reveal a different layer. Many young stars in the cluster emit strong X-rays from magnetic activity, far stronger than the Sun's current output. These emissions confirm their youth and high levels of turbulence in their outer atmospheres. Chandra also detects diffuse X-ray emission from shocked plasma, where stellar winds collide. The presence of this hot gas shows that feedback is not limited to optical ionization or infrared heating, but extends into the million-degree regime. X-rays influence surrounding gas chemistry by ionizing heavy elements and driving additional reactions. They also erode protoplanetary disks, linking stellar activity to planet-forming environments. Ground-based optical observatories continue to contribute as well. Instruments at the European Southern Observatory and the National Optical Astronomy Observatory capture wide-field images of the Lagoon Nebula, placing it in galactic context. Spectrographs on these telescopes measure velocities, line ratios and abundances across broad areas. Combined with space-based data, these measurements provide a consistent picture of the nebula's composition and motion. The wide-field surveys also trace how the Lagoon Nebula connects to adjacent molecular clouds and star-forming complexes in the Sagittarius arm, situating it within the broader spiral structure of the Milky Way. Each observatory not only adds data but also reduces uncertainties. For example, Gaia's precise parallaxes refine the distance to the cluster, resolving discrepancies between older methods. ALMA's high resolution constrains the mass of dense clumps more accurately than previous single-dish measurements. Webb's infrared sensitivity identifies faint protostars that Spitzer missed, filling in the census of stellar populations. Together, these advances narrow the range of possible models for the nebula's evolution, bringing theory and observation into closer agreement. Multi-observatory campaigns highlight the importance of collaboration. The Lagoon Nebula has been observed simultaneously in optical infrared and X-rays to trace events such as flares or outflows across regimes. Coordinated surveys ensure that data can be compared, directly aligning maps of stars, gas dust and plasma. These campaigns transform the nebula into a multi-layered dataset, allowing astronomers to test how feedback propagates from hot plasma to cold molecular gas. Without such coordination, each wavelength would remain isolated, offering only partial insights. Public outreach benefits greatly from these observatories. Images of the Lagoon Nebula from Hubble, Spitzer and Webb are widely shared, inspiring interest in astronomy and illustrating the scale of cosmic processes. These images, while carefully processed for scientific accuracy, also display vivid colors that correspond to different elements and wavelengths. The Lagoon Nebula has thus become one of the iconic targets, demonstrating how modern observatories reveal the universe. For scientists, these images are data. For the public, they are windows into the hidden workings of star formation. Despite these advances, challenges remain. Even Webb cannot penetrate the densest globules, leaving their interiors hidden. ALMA, though powerful, observes small fields of view at high resolution requiring mosaics to cover large areas. Chandra's sensitivity limits the detection of faint diffuse plasma. Future observatories such as the Next Generation, Very Large Array and proposed X-ray missions will extend these capabilities, probing deeper and sharper. The Lagoon Nebula will continue to serve as a key target for testing new instruments, ensuring that its study remains at the forefront of astrophysics. From Earth, the Lagoon Nebula can be seen with binoculars as a hazy glow. Yet the coordinated effort of observatories across the world and in space has transformed that glow into a rich three-dimensional model of gas-dust stars and feedback. Each instrument contributes one layer, and together they reveal the complexity of a living nebula. The Lagoon Nebula exemplifies how astronomy advances not by single views, but by the synthesis of many, each extending human sight into realms invisible to the eye. Even with decades of study and data from many observatories, the Lagoon Nebula remains a place of open questions. Some uncertainties involve the details of feedback, the processes by which radiation winds and magnetic fields regulate star formation. Others involve the efficiency of converting gas into stars, or the conditions that allow disks and planets to survive near massive stars. Still others relate to chemistry, turbulence, and long-term evolution. These unsolved problems ensure that the Lagoon Nebula continues to be a focus of research, not only as a spectacular object, but as a test case for the physics of stellar nurseries across the galaxy. One of the primary questions concerns the efficiency of triggered star formation. Observations show that bright rims and compressed shells contain young stars, suggesting that feedback induces collapse. But disentangling cause and effect is difficult. Did feedback compress gas that would otherwise have remained diffuse, or did it simply reveal collapse already underway? The timescales of both processes overlap, making distinction challenging. High-resolution age dating of stars within these rims may help, but uncertainties remain. The Lagoon Nebula offers examples of both outcomes, where some ridges clearly contain new stars, while others remain starless despite compression. Understanding the balance between positive and negative feedback remains an unresolved issue. Another open problem is the survival of disks and the potential for planet formation. Infrared observations reveal that many low-mass stars in the Lagoon Nebula retain circumstellar disks even near massive O-type stars. Yet theory predicts that ultraviolet radiation and winds should strip disks, quickly shortening lifetimes. Some disks show evidence of erosion with cometary shapes facing the cluster, but others appear intact. How long disks survive and whether they can form planets in such environments remains uncertain. The Lagoon Nebula serves as a natural laboratory for studying disk survival under harsh conditions. This question extends to broader astrophysics. How common are planetary systems in dense clusters where massive stars dominate? The role of magnetic fields also raises questions. Observations confirm that fields align filaments and help collimate jets, but their overall strength and influence are debated. Do fields significantly delay collapse, or are they secondary to turbulence? In some clumps, field strength seems sufficient to support gas, while in others, collapse proceeds despite magnetic resistance. Ambipolar diffusion. The slow drift of neutral gas past ionized components tied to field lines is difficult to measure directly. The Lagoon Nebula provides evidence for both magnetic support and magnetic release, but the precise balance remains unclear. Understanding this balance is vital for models of star formation efficiency across galaxies. Chemical complexity within the Lagoon Nebula is another unresolved area. Detections of organic molecules demonstrate active chemistry, but the pathways and abundances are not fully known. Do shocks from jets and winds create most of the complexity, or do icy grain mantles provide a more significant contribution? How do radiation fields alter chemical networks? The answers matter because these molecules represent the raw ingredients for planets and possibly life. The Lagoon Nebula, though younger than regions like Orion, already shows diversity in molecules. Continued observations with facilities like ALMA and Webb will refine these measurements, but for now the full chemical picture remains incomplete. The long-term fate of the Lagoon Nebula is also uncertain. Over the next few million years, the massive stars in NGC 6530 will evolve and explode as supernovae. Their shock waves will sweep away much of the remaining gas, dispersing the nebula. The cluster will remain, but will gradually lose stars through gravitational interactions, eventually blending into the general galactic population. Yet the details of this process depend on factors not fully known and the exact number of massive stars, their masses and their lifetimes. Whether the cluster will survive as a bound system for hundreds of millions of years or disperse more rapidly remains debated. The Lagoon Nebula offers only a snapshot, and its future trajectory can be modelled but not observed directly. Another open issue is the true initial conditions of the parent molecular cloud. How turbulent was it before star formation began? Was collapse triggered by external forces such as spiral arm density waves or nearby supernovae, or did it occur spontaneously? Answering these questions requires reconstructing the past from current evidence, a challenging task. The Lagoon Nebula may have been part of a larger complex of clouds in the Sagittarius arm, and star formation may have propagated across it. Observations of nearby regions and their relative ages may eventually clarify whether external triggers played a role. For now, the precise origin story of the Lagoon Nebula remains partly speculative. On smaller scales, unresolved questions involve the multiplicity of stars. How many stars form in binaries or multiples, and what fraction are ejected from the cluster? Observations show that some young stars have already been flung outward by gravitational encounters. The frequency of such events influences cluster evolution and the distribution of stars in the galaxy. Yet measuring multiplicity in the crowded Lagoon Nebula is difficult, especially for faint stars hidden by dust. High-resolution imaging and spectroscopy continue to improve the census, but the full multiplicity statistics remain incomplete. Uncertainties also remain in modelling turbulence. Numerical simulations reproduce many features of the Lagoon Nebula, but turbulence is inherently chaotic and difficult to constrain. Observations show velocity dispersions and shock fronts, but the driving mechanisms and energy dissipation rates are not fully understood. Is turbulence maintained primarily by winds radiation or gravity-driven collapse? How does turbulence scale from large cavities to small clumps? These questions are central to astrophysics, and the Lagoon Nebula provides one of the best natural laboratories for addressing them, but definitive answers remain elusive. Even distance scale and age, though, better constrained by Gaia, still hold small but important uncertainties. A difference of a few hundred light-years alters luminosity estimates for massive stars and changes mass estimates for gas clumps. While the current consensus of 4,000 to 5,000 light-years is robust, refinements may continue as Gaia releases new data. Similarly, the age spread of stars in NGC 6530 is still debated. Some studies suggest continuous formation, while others propose bursts triggered by feedback. The uncertainty highlights the complexity of real star-forming regions, which resist simple chronological models. These open questions are not failures of knowledge but signs of active science. Each represents a frontier where observations and theory meet and refine one another, the Lagoon Nebula stands as a dynamic environment rich enough to challenge models and close enough to study in detail. Its unsolved mysteries ensure that it will remain a key target for future instruments, from next-generation radio arrays to improved X-ray observatories. As new data arrive, each layer of uncertainty will be peeled back, revealing more about how stars and clusters form and evolve. From Earth, none of these uncertainties are visible to the eye. The Lagoon Nebula appears serene, a glowing patch against the Milky Way. But behind that appearance lies a network of questions about efficiency, survival, magnetism, chemistry, fate, and origin. Scientists continue to measure, model, and debate, knowing that every answer will lead to more questions. In this way, the Lagoon Nebula serves not only as a stellar nursery, but also as a reminder of the ongoing nature of inquiry. It shows that even nearby wonders hold mysteries yet to be solved, and that the process of discovery is as continuous as the nebula's own restless motions.